for the day. Congratulations on making it this far into Interferometry 101. So the talk I'm going to give right now, wasn't quite sure what exactly to call it, so I called it error recognition. Really the idea here is that those of you who have never worked with astronomy data before may not know, but there exist problems inside of data. And it's nice to be able to identify those problems because problematic data is problematic. Going back to my normal math review stuff, so hopefully everybody knows this particular distribution. This is a normal / Gaussian distribution. It's the astronomer's favorite distribution ever. Nobody correct me on that. It's generally the distribution that we always trust that we're working with. In part due to something called the central limit theorem, which basically states that if you take a random draw of data or values from a distribution with known variance and you stack together, you take the sum or the mean of a bunch of randomly drawn variables, it should converge to something that looks like a Gaussian with enough draws. And so we trust that we make, over the course of even a single integration, you're stacking together typically hundreds or thousands of data points inside the correlator, and thus you are generally trusting that the statistics of the noise of the distribution is something that looks like a Gaussian distribution. There are two other distributions that are nice to point out. One is the chi-square distribution, which is basically the sum of the square of multiple Gaussian distributions. This is a favorite of people who like to do model fitting. And then down on the bottom, there's a somewhat related distribution called the Rayleigh distribution, which is very similar to a chi-square distribution with 2 degrees of freedom, so-called. The interesting thing about a Rayleigh distribution is that the amplitudes of the visibilities are actually Rayleigh distributed. They're not normally distributed. And that will become important for reasons I will get to shortly. But just know that if you talk about amplitudes, it's not normal, it's Rayleigh. Or its more generic form, Rician, which is a whole other thing. Yeah, you you can maybe tell who's told me this particular piece of information before. You can spend a lot of time on bad data and not actually get a result out. Or worse, you can get a misleading result that you publish and then have to retract. So sometimes it is actually the case that having no data is better than having bad data. And this is definitely something that I think every radio astronomer who's been senior to me has told me. This was told to me by my advisor, Jeff Bauer, back when he was my advisor. I heard it from the late Don Backer. Basically, every seasoned radio astronomer, I think, shares in this sentiment. At least I don't think I've ever heard anybody object to this sentiment. So we need to be able to identify bad data. And there are multiple reasons why data can go bad. We know that there are systems on the antennas, on the correlators, in the IFLO distribution that can lose lock, turn off, lose power. All sorts of things can go basically mechanically wrong or electrically wrong, and those can cause glitches. There are sometimes contaminants. I think Derek made mention of parasitic noise during his talk. Basically, these are things that will produce spurious correlation in the data, so it looks like it's actually power, but it turns out it's some subsystem kind of interacting or seeing itself. There are errors that will affect the gain solutions in your data. And in fact, you can get errors of the gain solutions or calibration solutions themselves. There are errors in the noise estimates or in the so-called weights for the data. And you can inadvertently end up over or underweighting particular pieces of data. But probably most disturbing of all is that it's really not any one particular piece of this. It's the assumption that all of these things are good. You should definitely not have that assumption. The first observatory that I worked at, the motto was, don't panic, but assume nothing. there's always new, interesting, weird things you're going to find in data, and that's part of working on a research instrument. These things are not commercially deployed with billions of users. These are research cutting-edge instruments, and so they have new and exciting behaviors that they use all the time. So before I go any further, I will say for this first top part, we actually do have an automated fault detection system. We work pretty hard to try to detect that information. Those of you who have observed with the SMA before may have seen this page before. These are observing reports. And inside the online recording system, we typically record when things go wrong. We keep a log of when things are on or off, why there was time lost. We're always looking to improve this piece of the system. So if you happen to get SMA time and you notice that there's something weird or something that you had to correct after the fact, we definitely want you to get in touch with us because we want to make this as robust and easy to use an instrument as possible. And part of that relies on getting feedback from our users to know what it is when things have gone wrong. So what do you do with bad data? So there's kind of three generic strategies that you can kind of point to. So the first one is to just discard the data, sometimes called flagging the data. And the idea there is that you know it's contaminated, you don't want to spend the time to correct it or whatever, you just want to get rid of it, and you chuck it away. It's the most common way of dealing with bad data. It does carry a couple of risks that I'll get into in just a minute. The second thing that you can do is you can downweight data that you think might have contaminants or problems in it. It's a bit safer in terms of if you're not 100% sure whether or not data is good or bad. It can be a bit safer than essentially establishing an arbitrary threshold at which you're going to chuck the data. It does come with some sensitivity penalties because if you could precisely remove the contaminants, that's always better. But it can be safer to downweight data that you think is suspect rather than doing things that mess with the statistics of your data. And the final thing that you can potentially do is correct the data. There are lots of techniques for potentially correcting corrupted data. The kind of typical example that people point to with radio frequency interference, RFI, which is usually a problem at lower frequencies, although it's becoming more of a problem in the millimeter wave. You can use this technique called Wiener filtering, which removes essentially this coherent power and actually subtracts out this contaminant kind of human-generated power from your spectra, and you're left hopefully with just astronomical signal. So I'm going to focus on mostly the first item in this talk because it is so common, but I will make a couple of comments about 2 and 3 throughout the rest of the talk. So this is a typical plot that you would see in radio astronomy. Something versus amplitude. And the something is kind of unimportant, right? It doesn't matter if it's a spectrum, it doesn't matter if it's an integration, it could be source ID, it could be whatever. Generally speaking, when people are looking for weird things, they plot something versus amplitude. And the motivation for that is pretty clear. We're looking at extraordinarily weak astronomical signals coming from the sky. So if you see something that has a tremendous amount of power, you think, okay, there's no way that this could physically be something real. Clearly, I can check this data. So I want to do a little group experiment here, just to get your minds excited about statistics and interferometry. So here's some data with some contaminants in it. I won't tell you which data points have the contaminated data in it, but normally what one does is say, okay, things above X level, I would throw away. So who would throw away everything above 2? Nobody. Everything above 3, raise your hand. No. Everything above 4? 1? Okay, all right, good number. Everything above 5? Everything above 6? Everything above 7? And who wouldn't throw away anything whatsoever? All right. I like that optimism. So kind of showing you the contaminated data that's here, you can kind of sort of see that, okay, the high points are definitely made up of bad data. There's a kind of weird medium inner rim that has kind of a mix of good data and bad data. And then there's a range that has mostly good data, but definitely still has some contaminants in it. So what do you do with this? What do you do when you've got lots of contaminants mixed in with good and bad data? What's the right threshold to set? So there's this nice rule, and I apologize right now for the block of text, but I promise I'll go through everything. There's this nice rule called Chauvenet's criterion, which basically says the long and short of it is you want to set, if you're going to threshold, you want to make sure that the odds of you thresholding and eliminating something that's just a random noise fluctuation is not high. Basically, it should be a coin flip as to whether or not you're tossing a single noise-only data point. So the idea is that you calculate the statistics of this distribution, the mean and the variance. You determine the likelihood of the event that it is that you're looking at. So 3 sigma is about 1 in 300. That's the number of integrations in a typical SMA track. 4 sigma is 1 in 1600, so that's the number of channels in an SMA spectrum. 5 sigma is 1 in about 2 million, which is actually the number of visibilities in a single integration. And then 6 sigma is just about 1 billion, which is about the order of the number of visibilities in a data set. So these are actually numbers that are, they seem really large, except that compared to an SMA data set, they're not that large. You determine the number of unique data points. You determine how many data points it is that you're looking at. So if you're looking at 1,000 data points like we were looking in this previous plot, that's 1,000 data points. You multiply the likelihood by the number of unique data points. And if the answer that you get out of that is less than 50%, you can say with confidence, okay, I can chuck that because it's not likely that a randomly distributed value will generate that kind of noise-like event. So those of you who guessed between 4 and 5, congratulations. You meet Chauvenet's criterion. Cheers erupt from the back. All right, so that's cool. We've eliminated some stuff, but of course, there's still a lot of garbage that's sitting down here. So kind of what else can we do? Well, amplitude is only one domain that you can look at things in. And in fact, as Mark pointed out during his talk, the data that we have are not just amplitude-based values, but they're actually complex values. And so if you plot these in the real and imaginary domain, you can actually begin to see a little bit more structure take shape. And if you actually filter based, again, on Chauvenet's criterion, you see that you actually catch more of these data points, more of these bad data points. There's still some crud in there that you have to take care of, but it's definitely doing a better job of isolating data points that are clearly bad. This is kind of the best way, at least that I have, for dealing with thresholding. It's really trying to take as many good, unique perspectives on your data set as possible, trying to figure out a sensible threshold for them, and figuring out ways in which you can enhance the significance of the crummy data and trust that the rest of the data is basically normally distributed. So what do I mean by that? All right, so here's our nice real and imaginary plot. This is a bunch of data points. Imagine that we want to do some statistic or run some average over a bunch of data points. Let's say that these are all, each one of these belongs to an individual, 20 points per baseline with about 50 baselines. So you can just simply take the vector average of all of those baselines, of all those integrations across that baseline. And you can see that some things begin to pop up, although the red and the yellow pop up, the black and the green don't. You can actually take the scalar average, which is actually taking the average of the absolute value of all of the data points. This is okay, and sometimes it's actually mathematically very convenient because a lot of programs will allow you to take scalar averages. Ideally, though, you really would like to do something more like measuring the variance or measuring the chi-squared score, because that's a statistic that's very well understood. Every software package has things for dealing with chi-square distributions. And things, you know what the noise-like distribution should be. The final thing you can do is if there's some pattern to the data that you know about, you can actually, I call it reprojection here, but you can basically do some sort of scheme to try to tease out that little correlation. So you see that the green circles are moving around in this pattern in the real and imaginary plots that happens to relate to a particular fringe rate. And so if you know what that fringe rate is, and if you know that that kind of thing is to be expected, you can try to manipulate the data, take an average over the data, and have that thing pop out. That sounds like a very weird thing to do, except it's actually not all that uncommon at lower frequencies, particularly dealing with RFI. And in fact, it's something that we have at the SMA for dealing with particular problems. Oh, yeah, just want to point out, yeah, this is basically what I just said. So here's a plot. This is my favorite plot from all of grad school. And it is, what you're seeing in red here is that you're seeing coherent power that is the reflection of a reflection of the warm ground being detected by two different telescopes. It was a very weird geometry that just kind of perfectly allowed for this just chance alignment that was just a glint of light that two telescopes were seeing. What had to be done here essentially was, normally during astronomical observations, you do fringe rotation, you do fringe tracking. Things that are contaminants that come in from the observatory itself don't move like sources in the sky do. They stay kind of at rest. And so if you undo that fringe tracking, you can actually see power stack up. In this case, it was emission coming from the ground. There are contaminants though, parasitic noise. We have oscillators that are inside of our spectrum. And those things don't shift around like the sky does. And so if you undo this fringe rotation, you can see that stuff pop up. The important thing is not the particular details of how to detect this, but rather if you know that a contaminant or a problem has a particular signature, you can go searching for that signature. And then once you identify it, remove it. Anjani, you have a question?
You can do this, you said you can do this in Compass, but can you do this in IDL?
Yeah.
Oh, okay.
Yeah. It's, yeah, this particular thing you'd have to kind of sort of write your own routine for, but the generic thing of doing some sort of correction to look for a problem like this is kind of just generically true, right? You can muck with data in so many ways that it's amazing and terrifying at the same time. All right. One other point, we've only been talking about amplitudes, and for good reason. This is the real and imaginary distribution. On the right-hand side is the phase distribution. I don't know about you, but I can't really pick out any good points or any good set of distribution points here that makes a whole lot of sense to look at. And in fact, if I actually show you where the bad data is, it's very difficult to use phase reliably as a discriminator of good or bad data. There's very limited set of circumstances where this works, really only with the very strongest of calibrators where you've got lots of flux. And even then, you run the danger essentially of doing things, culling the data in ways that affect the statistics of your data set and can lead you to get a basically suboptimal calibration or suboptimal imaging. So in general, I tend to avoid using phase as any sort of discriminator of good or bad data, with one notable exception that I'll get into in just a second. One final thing, I've been talking about, I mean, most of the time we're talking about averaging down data sets because more integration time means deeper sensitivity. But you can take medians. Medians are always a nice way of dealing with problematic data sets. And they're much more tolerant to outlier distributions. There is a penalty in using a median, which is they're about 25% more noisy than a mean over a typical data set. But if you've got problem data like the green, like the red, or even the black, sometimes taking a median of a data set is a lot more trustworthy way of knowing that you've got roughly the correct value versus trying to do something very deep and taking a mean. So yeah, just keep that in mind. The final thing that I want to say here, though, is that sometimes when you really can't tell whether or not a data set is good or bad, you don't want to cull things, you don't want to pull out data if you don't have to, or do it in an arbitrary fashion. And so sometimes it's actually just better to downweight the data. There are different ways of downweighting the data. I know in Myriad, at least, if you have lots of phase scatter, let's say on a calibrator, it lets you rescale or reweight the data based on phase scatter. There are other tools essentially that allow you to look at variances and use them as a way of adjusting the weighting on the data set that you're looking at. Take advantage of those when you can. It comes with a little bit of a sensitivity penalty, but at least you can know that you're not necessarily doing something super weird to your data set. All right. So speaking of weighting or weights, so Mark kind of introduced this up above in the way that we use system temperature for calibrating the fluxes of the data set that come out. So this is S1, S2 is the flux that's measured on the 1-2 baseline. And you can see basically kind of where all these terms come in. It's some set of values times the correlation coefficient, that's that rho. And the correlation coefficient is just the correlator output for the cross correlation divided by the square root of the autocorrelations for the two antennas that go in. That stuff is not the particularly important stuff. The really important thing up here is the system temperatures for antennas 1 and antennas 2 up there. Those system temperatures are measured, as I said earlier today, by putting a piece of absorber in, measuring the power that comes out of the antenna, and then pulling it back out. Sometimes that operation can go wrong. Sometimes the ambient load doesn't go all the way in. Sometimes you get just weird behaviors happening. And so in the upper right here, you can actually see from a real data set, you can see the system temperatures while we're on some particular target. And there's two weird things here. There are these green data points that are really, really high. And then if you notice, there's this yellow line down here that's really, really low, very close to 0. And so if you were to go through and actually look at what the visibilities look like, the green data points are actually off the chart, so they show up way high. But you'll end up with this kind of weird smudging of data that comes up down at the bottom. If you see something like this, sometimes that means that your weights are off. It typically is the kind of thing that gets taken care of when you do gain calibration, but if you're looking for problems in your data before you do gain calibration, and you might inadvertently flag something like that. So just be aware that something like this doesn't necessarily mean that the data is bad. It also means that at least once, just once, you should always check the system temperature measurements as taken on the system and just look for weird things like that. Because it has a direct impact on the data, if you look at it, just make sure that there's nothing weird that pops out. It could save a lot of headaches further down the road. All right, another thing that you can use as a tool with uncalibrated data is looking at something called phase closure. And so the idea is I have 3 antennas, and so I have 3 unique baselines, and each of these baselines has a particular phase of the visibility that it measures. And so the phase for each baseline, ignoring the noise component for a second, is the instrumental phases of the 2 antennas plus this visibility phase. So that's just the noise-free visibility and what comes out of it. The way that you can combine this, or what's interesting about this particular set of triplets, is that you can actually combine this series of equations in a particular way so that when you add together 3 baselines, the only thing that's left over in terms of the phase component is just the visibility values, just the true visibilities that are here, and completely cancel out the instrumental phase that you don't immediately know for. So this is a really nice way to know what the system is doing absent any information about the gains for the antennas. Where this gets extra interesting is that if you have a calibrator or any point source at field center, and you put it at the field center, and you take a Fourier transform of that, you get, remember, center impulse is just a flat DC offset, and so the phase at any position of u and v is equal to 0. And so all of these things actually cancel out to 0. So the closure phase for point source at field center is 0. And this is actually a tool that we use all the time during real observations. So this is a tool called Core Plotter. Basically plots the data as it's coming in. It's uncalibrated. And you can see those big white dots are phased as a function of time. And you can see that there's some scariness in there and some choppiness. And you might say, how do I know that things haven't gone completely awry? Well, you check the closure phases. Beautiful, nice, solid, flat. The interferometer works. Observations can move forward. People can be relatively happy. So closure phases are a really important tool for checking and validating the data. There is a similar quantity for amplitudes that you can use. It requires 4 antennas, and it's a little bit more complex. It's a little bit noisier, but for a point source, the closure amplitude is always equal to 1. It is a nice way to check for things like sideband separation errors, other things that affect the amplitudes only. It's not a very commonly used tool just because it is noisier and sometimes a little bit more difficult to understand, but it is a tool that exists.
And then it's the weather.
All right, so after you've looked at the uncalibrated data, now it's time to look at the calibrated data.
Okay.
So this is a couple of quasars that we're looking at. On the left-hand side, this phase is a function, phase and amplitude is a function of time, and the right-hand side is a spectrum for our bandpass calibrator. And you can see the bandpass calibrator looks fine, but the data later on in the track looks kind of suspect. It looks like it's converging around 0 phase for a calibrator, which is what you would expect. But this is a good chunk of time. This is the only time where I would look at phase and say, okay, maybe you cut that out, or okay, maybe you downweight that data. Because you would expect all of the baselines together to be around 0. And so if you see this kind of flaring, it means that the weather is probably really poor. And at the very least, you should make sure that that data is downweighted. When you looked at calibrated data, you should also look at the calibration solutions. So these are gain solutions that come out of our prototype pipeline. Up top are the wideband gains and amplitudes, and then on the bottom are the bandpass solutions, the frequency-dependent solutions. Normally, these things should look nice, flat, relatively smooth. The gain amplitudes should be roughly equal to 1. If you see something that's very low or very high, that's a sign that something's not quite right. Arguably the most common problem that you might see is something like this, where you see this phase wrapping, sometimes looks a little sinusoidal, and that's potentially a sign that the baseline solution that you have for your track is not perfect, because the geometric correction is not perfect. And so this is a case where you should check online to see if there's an updated baseline solution or antenna position solution, because that will fix this. So finally, after all that's done, of course, you want to inspect your source data. There are lots of ways to look at source data. Again, mostly it's amplitude versus something. And you can look at the source data in a variety of ways. The way that you kind of interpret your source data depends a lot on what your source is. And so whatever you do, you should just make sure, just use a common sense and think. If you're looking at something that's relatively faint, you shouldn't see a whole lot of emission. If you're looking at a planet, don't be surprised if you see amplitudes that are really high. One of the most useful tools that I have in general is actually plotting amplitude versus UV distance. Generally speaking, almost always, as you look at longer and longer baselines, you will see less and less emission from sources because more and more stuff will get resolved out. And so this could be a really nice way to find baselines or even sometimes individual data points that have gone bad. And again, in very restricted circumstances, sometimes phase, but be very careful. So that's all I have for error recognition 1, so I'll stop there and I guess take any questions.
So in your previous slide, with the plot of the black sky, so what's up with that yellow theme? That's what's cut off sharply at 15?
Yeah, so that's a good question, actually. So in this particular case, this was a baseline, a particular baseline that had gone bad in a data set for reasons that are a little bit complicated, but basically have to do with phase switching. So if you see a single baseline that looks like that, sometimes that's a bad sign. Each color is a different baseline. If you see a bunch of things that are up together, sometimes it actually just means that one antenna was just really noisy. And so this is not a sign to get rid of that baseline or to get rid of data. It's a sign to just inspect further and see if you can find out why this thing looks noisier than it should be. Kevin.
Could you go back a slide or two? You said there's one slide where it started to go bad. Yeah, that one there near the end of the night. For that one, would you just discard it, or is it possible to maybe average over a longer time?
So in this case, you can average over a longer time, but it depends. So it depends on what's going on, right? There are cases where the weather actually gets to be so poor that averaging for longer actually causes more decoherence, which is why sometimes it's just better to chuck it, because no matter how long you integrate for, it's always going to be really noisy. Sometimes there are things that you can do that are kind of clever that will correct the calibrator data, but keep in mind you don't have always the same information about the source data, so you can correct on 30-second timescales when you're pointing at a right calibrator. You don't necessarily have that same information for, you know, extragalactic galaxy at redshift 2 that's very faint. So just keep in mind that if you do something clever with your gain calibrator source, those tricks may not work for your actual science target of interest. And so the phases on your science target, something like that. Anything else? All right, so in the interest of time, I'll stop there and I'll let David take over. He was talking